In section 2.1, we are going to use the fundamental identities. So we have already seen these, and we'll get a few more, and we are going to put them to use. I'm not going to do too much talking here. I'm going to get right into it because you really do need to see a lot of examples, and you need to try a lot of problems to get the hang of this. So we've seen these before, and what we have here are equivalences. So sort of like if we knew that x was equal to 5, then we know that everywhere we see an x, we can replace it with 5. So it's kind of the same thing here. If I know two things are equal, I can substitute one for the other. We'll also be using the cofunction identities, the even and odd identities also. So let's get into an example. So in this example, we're going to use the identities to evaluate a function. So we have one value that's given to us. We don't know the angle. All we know is the secant value of this angle, and we know that tangent is positive. So we're going to use this information to find all of the other trigonometric functions. You can certainly use a triangle here, but I'm going to go ahead and use the identity since that's what we're practicing. The easiest one that I think to find would be the reciprocal of the secant. So I know the reciprocal relationship between cosine and secant. Okay, so I'm using an identity here that involves both secant and cosine. So I know secant, and I want to find cosine. So I'm going to use this identity here, and I'm just going to plug in what I know about secant right there. All right, so I know that cosine of this u would be 1 over secant of u, and I know secant of u is negative 3 over 2. So I'm just plugging in, replacing secant with negative 3 over 2 because I know that they're equal to each other. All right, so that just flips this over, and I get negative 2 over 3. So there's cosine. So one out the way. Now I'm going to start thinking about relationships between the functions that I know and the ones that I don't know. So first one that comes to mind for me is one of the Pythagoreans. I know cosine. I can find sine that because I know that sine squared plus cosine squared equals 1. And now I know cosine, so I'm going to plug that in here. I'm going to replace cosine squared with negative 2 over 3. It's still squared. Okay, so these two are equivalent to each other. I just found that. This has to be equal to 1. So if I can solve this equation for sine, then now I know sine. So sine squared of u. Here I'm going to do the square. 2/3 times 2/3 is 4 over 9. And I'm trying to find out sine. So I want to get sine by itself. I'm going to subtract. So I want to think about 1 so that it has the same denominator as this other fraction. So 1 would be 9 over 9. I'm subtracting 4 over 9. That's going to leave me 5 over 9. So I'm almost done, but this is not quite what I want. This is sine squared, and I just want sine. So I got to undo that square. I'm going to take the square root on both sides. So sine is going to be the square root of 5 over 9. Now, I'm taking the square root, and so this square root could come out positive or negative. And so I need to think about what quadrant I'm in to determine which one. So what I'm told that tangent is positive. So that's either going to be here or there. So I'm in quadrant 1 or quadrant 3. They also tell me that secant is negative. Secant is the reciprocal of cosine, so it would be positive in the C quadrant, but everything's positive in quadrant 1, so I know I'm not in quadrant 1. Okay, so because tangent is positive, that puts me either here or here, but one of the other functions is negative, so I can't be here. Okay, so we're definitely in quadrant 3. Now, what I'm finding over here in the green is sine, and in quadrant 3, sine would be negative. Okay. So this is going to give me a negative, and I'm just going to simplify this a little bit. So a square root of a fraction, square root of the top over square root of the bottom, and I don't know the square root of the top, but I do know the square root of the bottom, so I can rewrite it as square root of 5 over 3. All right, so now we got sine and cosine. I know that I can use that to get tangent. That's the reciprocal identity. Says that tangent is equal to sine over cosine. And sine we just found to be a negative, square root of 5. 3. That needs to go over cosine with -2/3. So I'm going to flip the bottom one and multiply, right? So negative times a negative is going to come out positive. So I get a positive square root of 5/2. Double checking that. I'm in quadrant 3, so yes, tangent should be positive. All right, so now we got sine, cosine, tangent. We got secant, so we just need cosecant and cotangent, and those are not too bad. Let's go ahead and do cotangent. Cotangent is 1 over tangent. So cotangent in this problem is going to be 2 over square root 5. Make sure you check the directions to see if you need to rationalize the denominator. Okay, we got cosecant. Cosecant is 1 over sine. And we already found sine, so I'm just going to put that in place of sine in this identity. So negative square root 5/3. Or you could also just flip it. So cosecant of this angle is still -3 over square root 5. All right, next example, let's see if we can simplify this expression. So we're going to use identities, but also we can use any algebra that we know. So things that we know, like adding and subtracting fractions, factoring, things that we would do with regular variables, we can do here with these trig functions. So looking at this expression, I can see that there's something in common between our first term and our second term. So terms are separated by addition or subtraction. So here's the first term, this is the second term, and they both have a sign. So that lets me know that I could factor that out and see what's left over. So this is the same as if you had like 3x squared minus x, and we were trying to simplify. They've got a common factor of x, so we can factor out the x. So dividing it out, what would be left over is a 3x and minus 1. So these two are equivalent. If you need to brush up on your factoring, greatest common factor, factor in trinomials, like the reverse FOIL method, all of that, please do, because that would be really beneficial for you for this section and beyond. All right, so I'm going to factor here. I'm going to take out the common factor of sine x. So I'm dividing out the sine x from each term. And you can always double check your factoring by multiplying it back. So if I divide out the sine x right here, all that would be left is 1. So I've got cosine squared minus 1 on the inside. You can distribute that sine x back inside. It should give you what you started with. Now, I'm not going to stop here because I do see a relationship on the inside there that comes from one of my identities. So let me go back to the identities. Looking at these Pythagorean identities, I've got this one that has sine squared plus cosine squared equals 1. And I'm going to use that one. So even though it's not exactly what shows up in my problem, you can see that I can kind of manipulate this equation here to make it look like what I have. Okay, so our identity says sine squared plus cosine squared equals 1. And this is in there. So let's see how we can get it. They've got this minus 1, so maybe I could just subtract the 1. Let's see, if we subtract 1 on both sides, I put 0 over here. Okay, so now I've got what I'm looking for right here. It just doesn't have the sign on it. So let's subtract the sine squared off. So now I have cosine squared minus 1 equals 0 minus sine squared would just be a negative sine squared x. And now this is still true. This is an identity because I got it directly from this identity. But I can see more clearly the substitution here. I can take out cosine squared plus minus 1, and I can replace it with negative sine squared x. Okay, so I'm going to replace this with negative sine squared x. So that would give me the sine x on the outside. And then the part in parentheses, I am taking out the cosine squared minus 1 and replacing it with the negative sine squared x. I can do that because they're equal to each other. And now to make this even simpler, I'm just going to multiply these two together. So sine squared times sine x times negative sine squared x. That's just like x times negative x squared. that gives me a negative sine to the third power. sine times sine squared assigned to the third power. And I think this is as simple as we can get it here. Okay, I'm going to add one here with some fractions to make sure that we could add fractions if um, our numerators and denominators were trigonometric functions. Okay, so if we want to add these two fractions, we need a common denominator. So common denominator between 1 plus cosine theta and sine theta. I mentioned early on when we were adding some fractions that you can always multiply the denominators together and you get a common denominator. It is not always the least, but it is always a common denominator. The common denominator has to have every factor that shows up in each denominator. So make sure we're remembering the difference between factors and terms here. Factors are multiplied, terms are added or subtracted. So 1 plus cosine theta itself is a factor. So common denominator has to have that. And sine theta is a factor, so common denominator has to have that also. So this whole thing is our common denominator. So how are we going to rewrite these fractions so that they both have this as the denominator? Well, we're just going to multiply by whatever's missing. Whatever it doesn't have, it needs, we're going to multiply by it on the top and the bottom to make sure we're not changing the value of the fraction. So my first fraction, the denominator is 1 plus cosine theta. So what is missing from the common denominator is the sine theta. So we're going to multiply on the top and the bottom by sine theta. In the second fraction, the denominator is sine theta. So what is missing from the common denominator is the 1 plus cosine. Okay, so I'm going to multiply by what's missing. Okay, so multiplying that together. Sine times sine is sine squared. And with the denominators, I'm not going to multiply them through. I'm not going to do the distribution. Because when you get to the end, in order to simplify the fraction, it has to be in factor form. So if you multiply it together, you're going to have to factor it back out to be able to simplify. So I would wait until the last minute if I absolutely had to do it. And right now I don't. So I'm just going to leave it as two separate factors here. Multiplying in the second fraction. I am going to multiply on the top. So distributing this cosine, cosine times 1, and then cosine times cosine, but leaving the denominator factor. Now they have the same denominator. We can add the numerators. So we're adding sine squared theta plus cosine theta plus cosine squared theta, and just keeping that same denominator. Now we're going to see if we can simplify anything in the numerator. We can't add any of these together. They're not like terms, but I do see an identity in there because I see a sine squared plus a cosine squared, and we know that's equal to 1, right? So we're going to use the Pythagorean identity here. So this plus this equals 1. So what we really have up there is 1 plus cosine theta. Now to simplify it, I see a common factor between the top and the bottom. And so this is why I didn't multiply it together, because the only way you can see this is if it's factored. A reminder here, you can only cancel factors. So it would have to be written as a multiplication before you can start canceling stuff. You can cancel things that are being added together. But I can cancel here both of these 1 plus cosines, and what I end up with is 1 over sine. And I can simplify that even further because I know 1 over sine theta is cosecant. So I have simplified this all the way from those two fractions down to just cosecant. That is really going to benefit you in calculus. If you got to find the derivative of this, what we started with, it's going to be way easier to just find the derivative of cosecant. Okay, now we have a fraction, and we just want to rewrite it so that it's not a fraction anymore. So here's what I was talking about with the canceling. You can't cancel out those ones because the 1 in the denominator is being added to something. So nothing you can do to simplify this. We want to multiply the top and the bottom. And we're going to use the conjugate of 1 plus sine x. When you multiply by the conjugate, you usually get something that'll cancel out. So we're going to multiply the top and bottom by 1 minus sine x. That's the conjugate. So using the same denominator, but changing the sign to 1 minus. So multiplying that through, it's not going to change anything on top. But in the denominator here, I am going to multiply these together because I'm hoping something will cancel out. So this is FOILing, or it's a difference of squares. Maybe you see that, but multiplying everything in the first parentheses by everything in the second. So 1 times 1, 1 times minus sine, 1 times, well, sine times 1, and sine times negative sine. Because we use the conjugate, that middle term cancels out. See, the negative sign and the positive sign, add them together, I get 0. So they cancel each other out. And what I'm left with is 1 minus sine squared. Now, again, these things are being subtracted. We cannot cancel anything. But you may look at it and you may see the denominator and say, oh, it's a difference of squares. I can factor it. And you're absolutely right. You can. But that would put us back where we started from. So we don't want to do that in this problem. Instead, we want to use an identity. Because you see that sine squared, you see the 1. That's going to bring to mind the sine squared plus cosine squared equals 1. And I'm doing the work over on the side here just to verify that this identity does apply. So can I make it look exactly like what I have in my problem? So I have 1 minus sine x, 1 minus sine squared x. So let's see if I subtract sine squared x, then my right side is going to become 1 minus. So what is that equal to? It is equal to cosine squared. So here, you can see that 1 minus sine squared x is equal to cosine squared x. So I'm going to replace this in my problem with this. So rewriting it as 1 minus sine x over cosine x. Cosine squared. Cosine squared x. Now, problem said write it so that's not a fraction. We still have a fraction here. So what we can do now, we can separate this into 2 fractions. So this really means 1 over cosine squared minus sine over cosine squared. At every step, you can double check. Could I put this back together? Could I go back to the previous step? So if I were to subtract these two, they have the same denominator. I would just subtract the numerator. I would get exactly what I have in the previous step. So just double checking. I didn't change anything. They're still equivalent. Okay, so now I'm going to look at each of these fractions individually. See, can I simplify it? 1 over cosine squared. So I have an identity that says that 1 over cosine is secant. So this, what I have in my problem here is secant, but it's squared because I got cosine squared. If you need to, you could separate it again. You could write it as 1 over cosine times 1 over cosine. If that helps you see that this would be secant squared. And in fact, I'm going to do that for the second fraction, just to make it clear here. So we've got sine. If I split up this denominator, I can write this as sine over cosine. And then I still have 1 more cosine in the denominator. So I'll stop and make sure that what I wrote is still equivalent to sine over cosine squared. And it is, but this helps to see that what we have here is a tangent. Sine over cosine is tangent. And then 1 over cosine, again, is secant. So this will give me tangent times secant. And I see some more things that we could do to this, but I think I'm going to stop it here because the instructions just said, write it so that it's not a fraction. And here I have no more fractions, so we can call it done. Okay, so this one's a little bit different, but we're still just substituting. So we're going to plug in things that we know are equivalent to each other. So they're giving me a value for x, and they're telling me that this theta is between 0 and pi over 2. So in the first quadrant, everything's positive. So we don't have to worry about signs here. But they give me a value for x. So I'm just going to replace the x in 4 plus x squared with what they gave me. And this will be squared. Okay, and now I'm just going to evaluate this and simplify it as much as I can. So I'm going to go ahead and do the square. So that would be 4 tangent squared theta. Very important note here, you cannot just square root the 4 and then square root the 4 tangent squared separately. Let me show you why that is true off to the side here. If I had something like the square root of 9 plus 16, we know that that's the square root of 25, and that should be equal to 5. If I try to split it up and do the square root separately, then I would get 3 plus 4, which is 7, and we know that's not the right answer. So you cannot split up the square root this way. So we're not going to do it here with our trig function here. So instead, we'll try to use an identity to see if we can simplify it at all. I see 2 terms here, and they both have 4s, so let's try to factor out the 4. So dividing 4 from each term. If I just divide the 4 from the 4, I just get 1. Dividing it from the 4 tangent squared, all that would be left is tangent squared. All right, now 1 plus tangent squared, there's an identity in there. 1 plus tangent squared, this is the Pythagorean identity. So I'm going to use that one, and I'm going to replace the 1 plus tangent squared with secant squared. Now I have it written as multiplication, so no more addition in there. Now I can square root it. I can square root the 4, I can square root the secant squared. And so I get 2 secant theta. And now it is written as a trig function.